In this lecture, we are going to learn some important concepts for solving binomial probability problems. In these problems, there are n independent trials. That means we perform an experiment n times independently. For example, throwing a die n times or tossing a coin n times. And for each trial, we define two possible outcomes. Let's call them x and y. And probability of occurrence of x in the trial is p, and probability of occurrence of y in the trial is q. And because there are only two possible outcomes, p plus q is equals to 1. And in these problems, we are often asked probability that there are exactly r occurrences of x out of total n trials. Now, here we have not said anything about y, but that is implicit in this statement that when we have exactly r occurrences of x, then remaining n minus r occurrences should be of y. So, the statement exactly r occurrences of x is equivalent to r occurrences of x and n minus r occurrences of y, or we can say that in terms of y also, if we say exactly n minus r occurrences of y. Now, to find this probability using binomial probability theorem, we write this as probability exactly r occurrences of x. Then at the back of our mind, we know that it involves n minus r occurrences of y also. So writing this probability in terms of number of occurrences of x, we do n, that is total number of trials, c, number of occurrences of x, that is r, then probability of occurrence of x, that is p raised to the power number of occurrences of x, that is r, into probability of occurrence of y, that is q raised to the power number of occurrences of y, that is n minus r. Now this we could have also written in terms of occurrences of y. In that case, because we have r occurrences of x, we will have n minus r occurrences of y. So probability for exactly n minus r occurrences of y will be, and here at the back of our mind we know that there are r occurrences of x also. So this probability in terms of number of occurrences of y will be written as n, total number of trials, c, number of occurrences of y, that is n minus r, into probability of occurrence of y, that is q raised to the power number of occurrences of y, that is n minus r, then probability of occurrence of x, that is p raised to the power number of occurrences of x, that is r. And here, as we are claiming that exactly r occurrences of x is equivalent to exactly n minus r occurrences of y, then these two probabilities should be equal, and that is the case because from binomial theorem we know that NCR is equals to NC n minus r, and the remaining terms p to the power r and q to the power n minus r are same in both the expressions. So these two probabilities are equal because NCR is equals to NC n minus r. Another type of questions that we are often asked is of the form probability that there are at least k occurrences of x. And this we can find by breaking this down into exactly k occurrences of x, exactly k plus 1 occurrences of x, and up to exactly n occurrences of x. So this probability can be written as sum r from k up to n probability of exactly r occurrences of x. and that we can write as sigma r from k to n and c r p to the power r q to the power n minus r. Now there is another way of writing this probability, and that is in terms of complement of given event, and that will be equals to 1 minus probability of less than k occurrences of x, and that again we can write as sum from r equals to 0 to k minus 1 probability exactly r occurrences of x, and that will be equals to 1 minus sigma from r equals to 0 to k minus 1 and cr p to the power r q to the power n minus r. Now here in this sum from r equals to k up to n, we have n minus k plus 1 terms, and in this sum from r equals to 0 to k minus 1 we have k terms, and it is common practice to write the probability in terms of the sum for which number of terms are less, that is when n minus k plus 1 is smaller than k, then we will write our answer in terms of this sum, and when k is smaller than n minus k plus 1, then we will write our answer in terms of this probability 1 minus this sum. Similarly, the probabilities of the form that there are at the most k occurrences of x can be found by breaking down the event into events of the form there are exactly r occurrences where r varies from 0 to k. So the probability I can write is sum of r from 0 to k. This time I am adding from 0 to k because in this case we can have exactly 0 occurrences of the event, exactly 1 occurrence of the event, exactly 2 occurrences of the event, and up to exactly k occurrences of the event. So that will be probability exactly r occurrences of x, and that I can write using binomial probability n c r p to the power r q to the power n minus r. Similar to the previous case, this can also be written using the complement of the given event, that is 1 minus probability that there are more than k occurrences of x, and this again we can break down into simpler events of the form there are exactly r occurrences of x, and in this case our r will vary from k plus 1 up to n probability exactly r occurrences of x, and this I can write as 1 minus sigma r from k plus 1 up to n and cr p to the power r q to the power n minus r. And here note that in this expression I have k plus 1 terms, and in this expression I have sum of n minus k terms. So same as previous case, if k plus 1 is smaller than n minus k, then I will use this expression to write my probability, and if n minus k is smaller than k plus 1, then I will use this expression to express my probability.